My name is Ed Thomson. Today I'm going to talk a little bit about Git, the version control system, take a little deep dive into it. Can I see a show of hands? How many people are using Git right now? Maybe yeah, that's absolutely everybody. Okay. Keep your hand up if you've been confused by Git at some point in time. Yeah, again, absolutely everybody. So let's try to take a little bit of the edge off if we can. Again, about myself, my name is Edward Thomson. I'm a program manager at Microsoft, which means I don't actually write code anymore. I just kind of stay in Excel, Word, PowerPoint, and of course Outlook, at least at my day job. I do also act as the maintainer of the libgit2 project. If you're not familiar with libgit2, it's kind of a re-implementation of Git as a library so that you can host it in your own application. And it's used by people like GitHub, GitLab, and of course Microsoft Visual Studio Team Services to actually twiddle the bits in the repositories that you host there and do the low-level kind of stuff. So that's why I have to understand kind of how Git works at a deep down level, but why should you understand? My friend Emma talks a lot about teaching Git and learning Git, really the very getting started basics, and she tells people that the worst way to educate people about Git is to start out by talking about how it's just a directed acyclic graph, right? Because who on earth knows what that means? Not me. I actually failed graph theory in college. Whoops. But you can still be successful using Git even not having graph theory. But it is kind of the next level up to start talking about how Git works on the inside and in its internals. Because what you really find is that knowing Git helps you use Git. If you rewind a bit and look at how Git came about, if you look at its genesis, it was invented by a guy named Linus Torvalds. If that name sounds familiar to you, I hope it does. He invented a thing called the Linux kernel first. And he invented Git to help him manage the development of the Linux kernel. He was frustrated with the version control tools he was using, and he set out to do something a little bit different. And when he created Git, he set out 4 goals. First of all, it has to be fast. Second of all, it has to support a distributed workflow. There are people working on the Linux kernel from all over the world. Third, it has to provide safeguards against accidental data corruption. And if there's ever a doubt as to the direction the project should take, you should look at CVS, the concurrent version system. It's the version control system that he was using, as an example of what not to do. There are 4 things on this list, and one thing is missing. Noticeably absent is easy to use. And it's not. It's so, in fact, challenging to use that XKCD has gone and made fun of it. And this is totally honest. Like, this is an accurate portrayal of the state of Git today. Because Git is really hard to use. It has some weird commands. The checkout command does 4 different things. You know, the first time it's listed there, it checks out a branch. The second time, it creates a new branch. The third time, it checks out a file in your current branch. And the 4th time, it checks out a different file in a different branch. So really challenging. And if you use it wrong, it pokes back at you, right? There are some really strange error messages like, you're in a detached head state. Who on earth knows what that means? By the end of this session, you will. And if you try to figure out how to use it, if you want to go read the man pages, those are hard to understand too, because it contains sentences like forward port local commits to the updated upstream head. I swear to God, I read that like 3 or 4 times before I realized they were talking about rebase, the most fun Git command of all. So I want to pause real quick. I think honesty between you and I is really important in the short 60 minutes we have together, and I'm telling you a lie on this slide. One of these things is actually not in the Git man pages. The Git man pages are so dense and hard to understand that somebody has created a fake Git man page generator, which is tons of fun. They fed all the existing man pages into a Markov chain generator, and out pops random things that sound like Git man pages. I created this slide a while ago, so I'm actually not sure which one's which. I think it's the third one, reveal all downstream commits below the sent upstream paths. I think that's the fake one, but how on earth is that any different than the first? I don't remember. So, you know, go check that out, have some fun. It won't confuse you any more than the actual documentation. So it turns out, we talk about how Git is really powerful and important, and this notion that it's really hard to use doesn't exactly jive with that. And it turns out that the Git commands are just really the thinnest abstraction over the data model. So if you understand the data model, you understand a lot better about how Git actually works. So let's actually rewind, start at the very beginning. What is a distributed version control system? Well, distributed version control systems came about, in particular, in the open source world. Linus invented it to work on the Linux kernel, and in the open source world, people are spread out all across the globe working on the projects. I mean, that's not always true, but often it is true. And the thing about working in a very distributed team is that you don't want to have one central server, because where would you put it? I live in the UK right now, and I work with people in Germany and the US and Australia. If we kind of average that out, we'd probably put our central server somewhere floating on an island out there in the Pacific, and that's not going to work for anybody. So the idea of having to use a central server is really problematic in open source. And so the idea of a distributed system kind of flips that on its head. In a classic centralized server, of course, you have to talk to the server to do almost anything. Some really take it to the next level and make it so that if you want to just edit a file that you've already got locally, you've got to run checkout and talk to the server and ask it if you can edit the file. And there are good reasons for that, but not if you are working on an open source project and with people all around the globe. Okay? So the idea of a distributed system brings the entire repository locally. So you have everything local, including all of the history. So that means everything you do is local, even when you commit. And it's not until you actually go and share that commit, the changes that you've made with your coworkers, that you actually hit the network. And this notion, this idea, really underlines and defines how Git actually operates. And it informs the entire data model. Right? So the repository is actually architected in order to support this type of a workflow. And it's very, very different than a centralized version control system. Okay? So we often talk about the repository, and now it's time to talk about what it actually looks like. This is where we go a little bit more advanced, and we do start talking about the fact that it's a directed acyclic graph. So we can actually just take a look at what history looks like. Let's say I'm working on a project with my coworker Alice, and we've both cloned the repository, we've gotten it from the server, and we've both gotten the 3 commits. It's a real simple repository, it's something like Hello World. I don't know why you need 3 commits to do Hello World, but let's say, I don't know, maybe we internationalized here. So we both clone this repository and we get the 3 commits. And so that means in this distributed system, if I make a change and check it in, and Alice makes a change and check it in, we both are only checking into our local repositories. We don't actually see each other's changes until such time as I figure out a way to get Alice's change from her. Maybe she opens a pull request, pushes it up to VSTS or GitHub. Maybe she sends it to me in a patch over email because that's a thing Git supports because it's important if you're a Linux kernel developer and it's 1995. But anyway, somehow I get her commit and bring it into my repository. And then I merge her commit and mine, and I get the result. Very straightforward. This tends to be how we visualize Git working, as this sort of graph that kind of diverges and comes back together. And it turns out that that's exactly how Git history is stored. So here we are in our little repository. Very straightforward. And if I run git log, I can see that, in fact, I have brought Alice's change into mine. But when you run git log, it's not exactly showing you exactly how Git is storing this information. You're just seeing like this flat list of changes without any sort of structure to them. Right? Just commit after commit after commit. So the nice thing about Git is you can run git log -- graph, and it will show you the actual structure that the repository is taking. And so you can see commit 1, 2, 3, and then it kind of branches off into Allison's change and then branches off in a different direction into mine. And then it actually comes back together. So this is actually the way history is stored as this graph structure, right? So there are actually a lot of tools that'll show you this besides just Git Graph, actually. You know, we've got like, I think I've got Git Kraken running somewhere. This is a really good example of a visual tool that'll also show you this. I like to see the graph. I like to actually look at the graph and see how it's changing over time in most of my projects. It's not actually it's not actually perfect in every project because depending on like the sort of branching and merging structure you use, you can get into a bit of a headache. If you look at Git itself, they really like their branches. So you can see each of these little lines over on the left is an actual branch that eventually gets merged, and they go a little bit crazy. So so I like to look at the graph. I like to use git log -- graph to see the way the structure has changed over time, but it gets a little problematic on a really, really giant repository. Okay. So again, this is the graph or the DAG. What does that actually mean? What does it mean to be a quote-unquote directed acyclic graph? Well, there is some direction to the graph. That means it's moving in a certain direction. I like to model it as moving forward in time. Again, I don't want to lie to you too much. These arrows don't actually flow this way in the Git object model. We'll talk about that in a minute. I swear to God, one of the hardest things when you've decided to start writing a distributed version control system is figure out how to draw the arrows on the whiteboard when you're talking about things. I've spent countless hours of my life in these discussions. Well, so we'll get there in a second, but there is a direction to the graph, and we often model it as moving forward in time. And it's acyclic, meaning you can't have a cycle in the graph, meaning that one commit can't point back to a previous commit. So it's moving forward in time. You know, commit 3 can't have been the parent of commit 1. That doesn't make a lot of sense. As far as we know, time moves forward. So you can't kind of go back and change the directionality of time. Okay? That's all we'll talk about, the fact that it's directed or acyclic now. We'll just call it the graph. Okay? I think this is the last lie. There's something wrong with this slide. It's not so easy to go 1, 2, 3, 4, 5. In a centralized version control system, that's the way your commit IDs work. But that's not actually the way this works in Git. The reason being, they can't. If I'm working on my repository and I've cloned down the repo and I have 3 commits and it's at commit ID 3, and I go and make a change and check it in, and Alice goes and makes a change and checks it into her repository, how do we know who gets commit ID 4 and who gets commit ID 5? Right? We'd have to have some way to talk to the server and get that commit ID. So that's not actually how Git works. I think most of you have probably seen this. Git stores its commit IDs as a 40-character long hexadecimal string. What that is actually the SHA-1 hash of the commit. It's set up that way. You know, it could have been like a random number or a GUID, but using a SHA-1 hash actually makes a lot of sense. This was an idea inspired by the monotone version control system, who really set the groundwork for the way Git works in a lot of ways. So we take the commit and we hash it. We run it through SHA-1, and the resulting hash ID becomes the commit ID. And so you get things like, and thankfully we only have to talk about like the first 7 or so characters. So you get commit IDs like 1C, 6B, 201. So it's a little bit of a bummer, but you know, you usually only have to talk about like the first 7 characters, and on a big, like, I don't know, TFVC, like centralized version control system, you'll get change set IDs into the 7 digits. So it's not too much of a stretch, but it is a little bit of an annoyance, right? So what does it mean when I say we take a hash of the commit? What do I mean when I say of the commit? So a commit represents the entire repository. So it's a snapshot of the entire repository at any state and time. That's not always so obvious, because if you run git log, or if you run git show, for instance, what it'll show you on a commit is just the changes. It'll show you the diff of how that commit changed from its parent. So it's really easy to start thinking that that's what Git is actually storing, just the diff, how something has changed in a new commit. It's not. It's storing a snapshot of the entire repository. So when it's computing that diff, it's actually doing the diff every single time you run git show. Okay, so to make that structure, to make that snapshot, a commit is made up of trees and blobs. Trees are directory objects. They represent, file system entries, and blobs represent an actual file. So you have a bunch of blobs, one for each file in your Git repository, and they are organized into trees, and then a commit points to the root tree, the root of your Git repository. It looks something like this. So if I have one file, just file1.txt, it'll be stored as a blob, and it's hashed also. So we take the SHA-1 hash of the file that you're checking in, and we put that into a tree. This is the root tree, and we take the SHA-1 hash of that tree, and then a commit points to that tree. Okay. A lot of people seem to think that Git is inefficient because it stores a snapshot of the entire repository at every state and time, but it's not actually. This is where the SHA-1 hash as your ID starts to make a lot of sense. So if I have one file in my repository, file1.txt, we take the hash of that. Let's say I add another file and I want to check that in. I want to create a new snapshot that's got file1.txt and something else. I don't put another copy of file1.txt into the repository, because when I hash it, the hash is the same. Hasn't changed. I'm only adding file2.txt. So I get a lot of space-saving benefits. I'm just compressing the repository without even trying, because I don't need to add another copy of file1.txt when it hasn't changed. So to add a new file, we just put a second entry into our tree, file2.txt. The tree entry, it does change, right? It's a different tree now, so its SHA-1 ID changes. And then we create a commit on top of that. So we don't have to duplicate that at all. I think, so I've said, this is what a commit is. It's a copy of the content. Let's actually take a look at what it's storing on disk. Again, let's get back to my actual repository. So this is my working directory. I've got a bunch of files in it. I've also got this folder up top, .git. That's where Git actually stores all the metadata. That's where my Git repository lives. I don't know if you've taken a bother to go look inside. It's got a bunch of files and folders in it. This is actually the metadata of your repository. And the commits, the trees, the blobs, the things that make up our repository, we call those objects, so they're in the .git objects directory. We'll talk about a couple more of these files in a little bit. And if I look in .git objects, I see a bunch of hex characters. These are where my objects are stored. When I first start creating objects, they're stored in here as loose objects, they're called. And it's basically just one object per file on disk. Later, Git will come along and pack these up into an archive, which allows it to be a little bit more efficient in the way it accesses objects. But when you first start creating them, they're stored as loose loose objects on disk. And if I actually just go and read one of these, I'll see my file. Oh no, I won't actually. I'm really disappointed. Turns out that Git compresses it. But Git does give us a bunch of handy utilities to actually look and inspect the objects that live there. This I know happens to be a commit, so I can run git cat file commit, give it the ID that I'm interested in, and it'll show me. So this is what I mean when I say we take a SHA-1 of the contents of a commit. This is that commit. So a commit contains some metadata about when I made the change. It was me on this date. It gives me the commit message. And then up top, I see the tree. So this is actually pointing to the root tree, the snapshot of my Git repository when I ran this commit. And it's also pointing to a parent. So that is how Git builds its tree structure, how it builds the graph in memory. It starts at one commit, and then it can walk backwards through the parents. Okay, so that's what I meant when I said that we get into arguments over which way the arrow should go. Git actually points backwards. It points to the previous commits in time. Okay, and we can look at these other objects. We can look at the tree. If you run git cat file tree, is what you would expect to happen, like git cat file commit. If you do that, you're really bummed out because it's also in binary. Turns out that Git stores trees in a binary format in order to save a little bit of, make it a little bit more efficient. Instead, I can run git ls tree and give it the ID, and then I'll actually see what my tree looks like. Again, I've got file1.txt and file2.txt at this revision at those IDs. And I can run git cat file on a blob being a file, of course, and see the actual contents of the file at this point in time. Okay? So all cat file really does is kind of just uncompresses the object or finds it in the pack file if Git has stored it in the archive and just dumps it to screen. So it's really handy for inspecting your Git repository. So that's how objects are stored. That's kind of the minimum thing you need to be a version control system, is to be able to take copies of files and store them at a particular version. But it's not so helpful if that's all your version control system does. You also really need the ability to make branches, because if I'm working on some like long-running feature, let's say I'm hacking something in and it's not quite ready to ship, and my coworker Alice needs to fix a bug, we need to be able to separate our workflows. I need to be able to keep working on that development feature that isn't ready to ship so that Alice can, get her code into production, fix that critical bug. And so that's the, kind of function that branches perform. Branches work a little bit differently in Git than they do in most centralized version control systems like Subversion or TFVC. In those sort of version control systems, you have a folder, and you branch a folder. So in TFVC, you'll often see it called main, I think. It's been a long time since I've used it, apparently. In SVN, you tend to talk about trunk as your main folder where everything's integrated. And next to trunk, if you look in your repository, you'll see other branches. You'll see feature branches, you'll see release branches. That's not the way Git stores branches. Git actually stores branches at the repository level. So you branch the entire Git repository when you create a new branch. And that's actually really, really economical in Git. So we've talked a little bit about the graph. Why does Git store branches this way? Well, it turns out that instead of actually branching folders inside the repository, Git can store a branch really, really economically just as a pointer into this graph. So if I have my branch in this repository that we've been working on, what Git's actually doing is just storing a pointer to the commit that my branch is currently referring to. And the same with Alice's branch. So that it's a pointer into the graph. And the nice thing about this is that since it's lightweight, since it's easy to, just make a pointer, right? You just kind of write a file on disk. We'll see what that looks like in a second. But because this is so lightweight, it encourages you to branch more. So working at Microsoft, I've worked on TFVC, and we worked in a really big repository. The TFVC code base is pretty large. It's not huge, it's not Windows, it's not Office, but it's pretty big. And so to create a branch on our centralized version control system would take, I don't know, an hour to like copy bits around and line everything up. And so you had to do it, only when you needed it. And you had to get an administrator to do it because there was so much overhead, yada, yada, yada. Terrible system for the idea of topic branching, right? If I just want to fix a bug, I can create a branch to do that. You would never do that in TFVC on a big repository. It would just take too long. In Git, it's super easy because a branch is really just a pointer. What do I mean when I say that? So let's go back into our Git repository, into the .git folder where all the metadata is stored. And right below the objects folder is a folder called refs. And in Git terminology, a ref is a branch or a tag. And again, in Git terminology, it's actually not called a branch, it's called a head. So I apologize for that, but if you look inside your Git refs heads folder, you'll actually see the branches. And so they're actually named on disk, the files on disk are named the name of the branch. So it's really super easy to inspect these. And I can look at what's inside. The fact that it's 41 characters might give some of you a hint as to what's in there. It's the SHA-1. It's the commit ID that this branch is currently pointing to. And I can look at mine, and I'll see that it's pointing to a different SHA-1. And if we look in our log, and we pass the decorate flag this time, we can see that, in fact, my branch, the one on top, is 9969 whatever, which corresponds to the contents of the file. Alice's branch is 1C66. So it stores these branches just on disk in these files. So it's really easy to manipulate these. It's really easy to create a new branch. All Git has to do is write 41 characters to disk, and boom, you have a new branch. Way different than needing an administrator, taking hours to set something up. So it really encourages you to create more branches, even just to fix a bug. I create a branch. So it's great that we have branches, but usually you have the notion of being on a branch. I'm working on some branch. When I check in changes, they go into my branch. When Alice checks in changes, they go into hers. Git uses another type of branch for this. It's called a symbolic reference. And the important one is head in all uppercase. If you've ever been in that dreaded detached head state, this is what it's talking about. We're starting to get into that. So head stores the current branch that you're on. And again, it's also just a pointer, but instead of being a pointer to a commit, now it's a pointer to a branch. And I can look at my head file in all caps in my Git repository, and it says refs heads mine. So this is telling me that I'm on the mine branch right now. And if I run git branch, indeed I am, right? So Git, to tell you what branch you're on, just looks at the head file, says refs heads mine. It can then figure out which commit that is by looking at that file, the mine file. If I switch branches, say to Alice's, all it's going to do is update that head file. Okay, so super straightforward to change branches. Obviously, it'll also check out the differences between Alice's branch and my branch. That's the time-consuming part, but switching branches is really straightforward. Let's go back to mine. So branching is great. We need to be able to branch so that Alice can fix her bug while I'm working on my feature. But branches are pretty pointless unless you can actually converge at some point in time. And of course, in Git, that is merging. So in our repository, if we look back to before I had actually brought Alice's change into mine, what happens is to figure out how to get these changes in, first we have to find the common ancestor. And in a centralized version control system, when you create a branch, that information gets stored in some database somewhere. And when you do a merge, that information gets recorded too. And then the centralized system can figure out how these branches diverged over time and where your common ancestor is. It's not always easy, especially if you have some advanced merging capabilities to figure that out. In Git, it's super simple. You can look at the graph and see it, right? Alice's change is there, my change is there. Let's just walk backwards until we find the first common commit, the first commit that we both have in our repository, and boom, that's our common ancestor. Easy. Once Git finds that, then it can figure out how to do the merge. So it looks at the common ancestor, it looks at the files that are inside of them, and then it looks at each of the branches. And it just goes straight down the list, enumerating them. What file is in my common ancestor? Has it changed in my branch? Okay, What about their branch? Okay. So for files that have changed on one side but not the other, it's super easy to just take them. You just take the changes. If file 1 changed on my branch and didn't change on their branch, we'll just take file 1 into the new repository, into the new merge result. Same with file 2. Over here, file 4 changed on their branch, but not on mine. We'll take that. File 3 hasn't changed anywhere. It just stays the same. So merge is actually very straightforward until you merge this, until both branches change the same file. That's when it gets a little trickier. But at its root, it works the same way. You look at the file and the common ancestor, you look at the file on each side, and you just go line by line. Did this line change in one branch? If so, let's take that line. Did this file change in the other branch? If so, let's take that line. This works most of the time, right? This is really pretty naive, because if one branch changes the way a variable is declared, changes its name, but doesn't touch any of the other, maybe it doesn't change the bottom of the file. So it changes the name of a variable, and it updates that variable every time it's used. But then somebody in another branch appends a new function at the very bottom of the file that references the old variable name. Obviously, AutoMerge can't sort that out for you. It'll take the changes from one branch and it'll take the new use in the other. So you still need to check your AutoMerge when it's done. You need to, run your unit tests, and obviously this is just a best practice in DevOps these days. I probably don't need to tell you this. But for the most part, AutoMerge, despite being really naive, works really well. Of course, if both people change the same region of a file, you'll get a conflict. I'm sure we've all seen this. There are good merge tools, of course. I like SourceGear diff merge, but find a merge tool that you like, unless you really like using VI and cleaning up arrows all the time. And if you do, please do yourself a favor and turn on merge.conflictstyle diff3, because at least you get to see the common ancestor then. It'll provide you a little bit more context when you're suffering in VI, trying to figure out how this file changed and where these conflicts came from. Okay, this is actually what I use most of the time is VI. Yeah, whoops. Old habits die hard, I guess. So once that gets computed, once all the files are auto-merged and the new tree is computed, once you've resolved any conflicts, when you run git commit, what Git will do is actually create a new commit, with two parents. We saw earlier how Git encodes the parent in the commit. When you do a merge, Git records two parents. Let's take a look. So let's go back in time to before we had merged Alice's change into our repository. And I can run git log -- graph -- one line -- decorate. And we can see that right now I don't have any of Alice's changes. I'm getting really tired of typing git log -- graph -- one line. It's super useful. I've got it aliased, git LOL, log one line. It also comes in handy when you're working in a source tree that doesn't make any sense. You get to run git LOL and give yourself a little smile every time you're like, what happened in this history? But if I can also add the branches flag to git log -- one line, and I'll see all the branches that exist and how they relate to history. So I can see right now that Alice's change is built on commit 3, and so is mine, but we haven't merged it yet. So let's actually do that merge. Okay. Like I said, I really do spend a lot of time in VI. So once I've done that, I can run git LOL, and boom, we've got our branches diverging and then coming back together. And if I git cat file commit, the new commit, we'll just use head, I can see I've got two parents. So this is actually how Git builds this graph structure, right? It starts at head, and it starts walking, finds the tree, finds the commit information, rather, that head refers to, and then it opens up the parents, and it just keeps walking down that list to build the graph. So when I run git log, that's actually what it's doing. It opens the head file and then keeps going down that list. Okay. That's the typical merge case. You may have seen something called a fast-forward merge. This happens especially if you only create topic branches off of master, your master stays in sync with your server, the master on your server. When you run git pull in that situation from master, you'll see this was a fast forward. So what does that actually mean? If we look at Git's graphing, we can see that really quickly. Let's say Alice has made a change here, and I haven't made a change, right? I cloned the Git repository, I haven't done anything, and there's a new commit maybe on the server. When I run git merge in this scenario, by default, it'll be a fast forward. All Git does is update the pointers. So again, let's go back. And so what we can see now is that if we look at Alice's branch, it's on top. My branch is right below it. So we have a linear history to Alice, right? We're not on Alice's branch yet. We don't have any of that change. She's a commit ahead of us. If we just look at our history, we'll see that. But what we don't see this time, despite using the -- graph, is any sort of graphical divergence, because there isn't. It's a straight line. And so if I run git merge Alice, it tells me that it's a fast forward. So literally all Git has done here is update my branch to point to the new commit that Alice is on. And head, of course, hasn't changed. I'm still on my branch. And if I run git log, I can see that. All it's done is update these pointers. So fast forward merges are super efficient in Git. All it has to do is calculate that it can do it. It'll set the new pointer up. You can, if you don't want to fast forward, you can pass no fast forward option to merge. That's the way, if you've ever seen like maybe GitHub or VSTS, when you click commit pull request, it will turn on that option. It will not do a fast forward intentionally so that you can see the information of when the pull request was committed. Okay, so you can turn this off, but I don't know why you would. It's a great feature. So that's merging. That's probably the most common way people take two branches and join them up. There's also another feature, which is the subject of much sort of religious debate, if you will, and that's rebasing. And a lot of people are frightened about rebasing. It's not, at its heart, it's not all that challenging. The idea is, and this is where the name comes from, you have some commit, my commit, and I want to integrate it into Alice's, but instead of merging it so that I have a new, a join in the graph where I have two parents, I want to just pluck this commit off, and I want to base it off of Alice's commit. I want to change how it exists in history, hence the name rebase. And at its heart, all we do is we, again, find the common ancestor, we find the set of changes that were uniquely introduced in this commit, and we just replay them right on top of Alice's branch. It sounds pretty straightforward. It is pretty straightforward. The problem comes when you've got a lot of commits, when you've diverged a lot, and you end up with conflicts. Since you're replaying every commit back on top of Alice's branch, you end up trying to solve the same conflicts over and over again, quite often. So it's not perfect, but in theory, in the graph, it's really quite straightforward. So let's take a look at what that looks like if we had rebased Alice's change instead of merging it. Okay, so yeah, we've got Alice's change diverging from our change, and let's do something a little bit different here. Let's actually create a conflict so we can see exactly what's going on. We can see by running git diff that Alice has added a new file called alice.txt. Let's also create a file called alice.txt. We don't have one right now if we look. Okay, so now we've got a file, alice.txt. Indeed, we will have a conflict. Let's add it to our repository. And rebase. So when you actually stop and look at the messages that Rebase is giving you, it gives some insight into the process. First, it says, applying my change. Okay, so what it's actually done is, in this case, created a patch file of Alice's, of my change. And if we look in our rebase folder, we can actually see these patches that get constructed. You know, I don't think you should never ever need to do this, but it does illustrate the way Rebase works. It creates a new patch file, and then it's going to apply this patch and commit the changes. So that is the first commit in the Rebase. The second one we introduced are conflicting alice.txt file, and that's where it stopped. If we scroll back up, it tells us that we had an add conflict. So Alice added the file alice.txt. I also added the file alice.txt. And so it's just left us in this indeterminate state. If I look, I do have an alice.txt, and I have both sides with the fun arrows and the conflict markers. So at this point, I need to edit alice.txt. I'll take both changes, and then I can git add and git rebase continue. Let's scroll up again. We skipped over the very first line in Rebase's output. It says, first, rewinding head to replay your work on top of it. So what it means there is it's taken our head file, and it's pointed to the common ancestor. Sorry, it hasn't. It's pointed to Alice's change. And then we're going to apply each one on top of that. And the way it does that, instead of checking out Alice's branch, is by checking out the actual commit. What do I mean by that? If I look at my head file, I'm not pointing to a branch anymore. I'm not pointing to Alice's branch. I'm pointing straight to a commit ID, as if head were just a regular old branch. This is what a detached head is. It's when you somehow have gotten into a state where your head file isn't on a branch anymore. You are detached from a branch. You are in a detached head state. So if I were to just do something crazy, like try to get out of this rebase, right? I've decided that these conflicts are terrible. I don't want to deal with them anymore. I should have merged instead. I want to get out of this. The right way to do that is to run git rebase -- abort. That'll just stop everything, and it'll get you back on the branch that you were on to begin with. It'll just undo all of this crazy state. If I don't do this, if I don't abort my rebase and try to kind of keep going and try to figure out a way to live life as if I had never gotten into this mess, I will still be in a detached head state. You can stay in a detached head state. So let's do something crazy in our Git repository, and we're not rebasing anymore. We're just blowing away metadata now, right? So, oh my God, if I run git status, it says head detached. And I can pretend to keep going. And git log seems to work, but ultimately I'm not on a branch. So don't go down this road. You can also do this if you check out a commit by its ID. And I know this is probably the most common way to do it, because checkout is a confusing command. There's like 4 different ways to invoke it. If I just check out, sorry, let me type that right, then you can also get into a detached head state. And it's getting better about warning you about what's going on and what this means, but ultimately it's still rather easy to get into this case. So don't do this. Stay on a branch. Always check out branches. Cool. So that's where we ended up, right? So we've talked a lot about the actual .git folder and what's inside, what your repository kind of looks like under the hood. What we haven't talked about is the way that you tend to actually interact with your Git repository on a day-to-day basis. You don't spend most of your time in a folder called .git. You spend most of your time with your source code in your working directory. And the working directory itself doesn't have much interesting going on about it. I mean, your source code, of course, is interesting, but from Git's perspective, they're just files there, and it manages them. What's interesting to Git is a file called the index that maybe you've heard of. It's got 3 names, like everything in Git it's confusingly named. It's called the index or the stage or the cache. What do these things actually mean? So from Git's perspective, the stage is what's going to be your next commit. If you were to run git commit at that very moment, everything in the index would become that next commit. And again, Git doesn't store differences. It doesn't store how your files changed from commit to commit. It stores a snapshot of the commit. And you can run git diff to figure out how things changed, but it's a snapshot. And just like a commit is a snapshot, the staging area is a snapshot. So when you run git add, it puts files into the index. When you run git rm, it removes files from the index. And otherwise, everything in the index is what's going to be committed. So remember ls tree, that's what told us what is in our, here, I'll put this on top so it's easier to see. We used git ls tree to tell us what was in the tree at a specific time. I can pass head to it, and it'll tell me what's in head right now, what's in my repository that was checked in at the last commit. And if I run git status, you'll see that I haven't changed anything in my working directory. I can also run git ls files -- stage, and it'll tell me what's in the staging area, what's in my index. And they're identical at this point because I haven't made any changes. My status is clean. So you'll see that all those files exist in both places, and they're at the same IDs. Okay? So what Git's actually doing is just diffing these two things to show me status. And if I make a change to a file, I wasn't suitably excited when I wrote this file. Let's change that to an exclamation point. And if I run git add, we can look at the staging area. And file3.txt now has a new ID. So when I ran git add, it's actually computing the ID of the new file and putting that new ID into the index. And if I run git status, it will actually compare what's in head to what's in my index. And that's how it determines what I've modified. And now, once I run git commit, I can run ls tree head, and it's updated head now with that new commit. So if I want to see what's changed between my current version and my previous commit, I can run git diff. What that's going to do is inspect the trees, find the file 3 has a different ID in one, and just show me that difference. Okay. So Git actually does store in the index a whole snapshot of the files that will be committed. And when you run git status, it's actually comparing everything. So it compares what's in the working directory to what's in the index, and those are your unstaged changes. Those are the changes that you've made that you haven't yet run git add on. And if you ran git commit, those would just stay behind, right? Because the index is what will be the next commit. If I compare my index to my head, those are my staged changes. Those are the things that I've run git add and git rm on, and those will be the next commit. So Git just basically is a big diff engine. It just diffs everything against everything to show you what's going on. And especially when it comes to the working directory, that sounds really inefficient, right? I've got to crawl the entire working directory, comparing it to what's in the index to tell me what's unstaged. That is where the index gets its other name, the cache. So what actually is stored in the index is metadata about what's in the working directory. And that allows Git to not have to open every single file and compare it to the index. Because remember, the index just has the SHA-1 of the blob. And so to do a comparison against that, you would have to SHA-1 your entire working directory. That sounds terrible, and in fact it is. And that's not at all what Git does. That's what allows it to stay fast. We used ls files -- stage before to show us what's in the index. We can use ls files -- debug, and that will actually show us all of the bits that are stored inside the index for every file. And you'll see things like ctime and mtime. You'll see the inode number. You'll see the size of the file. So what Git can do is just open your working directory, and it can compare the timestamp that it's got in the index against the timestamp that it has on disk. And if that timestamp hasn't changed, if the size hasn't changed, the inode number hasn't changed, nothing has changed, Git can just skip it. It will know that you don't have any unstaged change there. So it can just keep going, doesn't have to actually open the file or calculate it. If I change the timestamp and I don't actually change the file, so now file1.txt has a new timestamp from what it had before. Now Git will actually have to open up the file, hash it, see if it's changed, and actually do the comparison against the index. But until I do that, until I make some change, Git can just skip right over it. It's really handy. One thing that you tend to do, so when you run git add, you add a file to the index. So right now I'm at 5C11 and I haven't actually made a change. So if I make a change and add it, one thing that you can do is if I run git add, so it's going to hash this, and Git's not going to go bother hashing the file to get the ID and not also save a copy, right? So when you run git commit, it's already prepared all the objects that it'll store. It just writes a new commit. And if I run ls files -- stage, I can see that new ID. It's OE2F744. The thing is, what happens if I run git add again? That file's gone now, right? It's not in my working directory for sure. If I run ls files -- stage, file1.txt is at a new ID. What happened to 0E2F? So it turns out that this is now garbage in the Git lexicon, and eventually Git will garbage collect it. But until it does, it's still in my object database. If only I had a way to get to it. There is. I actually just whipped this up. The last time I gave this talk, somebody asked, well, what happens to those files? And I said, well, I guess you could figure out a way to get them. And so finally, I came up with a little script called Git Recover. If you run Git Recover, it will show you the garbage that you've recently added to your repository, but that isn't there anymore. So it'll find the unreferenced blobs, the unreferenced objects, and show them to you and allow you to recover them. It's like, if you're old like me, you might remember Norton Unerase. It's like that for DOS, only for your Git repository. So I can run Git Recover, and it'll show me all the recently changed files that are no longer in my Git repository. And it sorts them in date order, so I'm guessing that the one on top is that file that I just added. If I type its ID right, 0E2F744. Oh, right, sorry, git cat file blob. Right, so that's the change that I didn't in fact lose. It's still hanging out in my object database. And I can git recover it, and it will just put it on disk for me. So I can get these files back after I thought I'd lost them. I can also use a quick interactive mode, and it'll just show me all of the changes that I've made, that I run git add on, and that I don't have currently pointing to by a commit. So you can get your lost blobs back really easily. No, I don't want that one. Let's take that one. And it'll just write it to disk. So super straightforward, nice way to be able to recover things that you've lost. So just remember to run git add on things. You know, the mantra of Git is commit often, but even more so, add often. If you're ever at a point where you have a snapshot of a change that you want to save, run git add on it. It'll stow it in the object database, and you can come back and get it later if you need it. Okay. Cool. So remember, the git commands are really just a simple abstraction over the data storage mechanism. So once you understand how that data storage mechanism works, you can be much more effective using Git. All of a sudden, when you have to type head in all caps, now you'll know why. It'll give you a lot of insight into the way it works. I think I've still got 5 minutes. Are there any questions? That hand went up quick.
Yeah, it showed the thing with when you get add. How does that compare to Git Stash?
Oh, so the question was, how does Git add compare to Git Stash? That is a great question. So what Stash actually does, so I'm not a Stash user, so I may screw this all up. We'll see. So what Git Stash actually does is it takes a copy of the index and creates a commit from it, but it doesn't put it in the graph, right? It doesn't create a new branch. It actually stows it away in a file called stashes. So let's see, file1.txt, make a change, git add it. I don't have to add everything to my stashes because I can stash unstaged changes as well, which is kind of a clever feature. So let's call it new file. Git status. Okay, so now I've got, and in fact I had that recovered garbage from before. So I've got a couple of files that are unstaged. I've got one file that is staged. Yeah, I'm sorry. I've got to read the man page on this one. I know there's a way to create a stage with, include untracked. So I can git stash save -- include untracked. And what's happened is that Git has now cleaned up my changes. So I can use the stash command if I am ready to, if I'm working on something, I get interrupted, and I need to make some critical bug fix, but I don't want to lose what I was working on. One thing you can do is just run git commit on your branch. That is almost always what I do instead. But you can also run git stash. It's just which one you prefer. What Git actually has done here, if we go into the Git directory, now we have a Git refs stash. It's not Git refs heads. That was our branches. We've got a Git refs stash. And so it's made a special commit for us that has multiple parents. Even though it's not a merge, it uses the parents to figure out what was unstaged, what was staged, and what the true parent of our commit would have been. So we see things like that. That's our true parent. And then it's made this sort of, we call it a synthetic commit. And it keeps the actual contents of the index as it was when I ran git stash. And I can even look at that. And I'll see, this should be my staged changes. Yep. So file1.txt is actually different. It has a different blob ID. It took me a while to actually find that. And so if I unstash, what will happen is it will take this tree and turn it into my index and put anything that was in the untracked files list, which is the other tree that's up there. It'll put that back on disk. Git stash pop, I think. Yep. Wow. I'm surprised I got that right, to tell you the truth. So stash is a little bit different. It is kind of like I said, it's not something I actually use. I think the best practice is just to create commits on branches, and then you can switch back and forth between those branches. But you can't commit untracked files. That's the advantage, the big advantage I see to stash. So I I don't want to keep you all. I'm actually out of time. If you do have other questions, I am super happy to answer them. I get a sick pleasure out of talking about Git, it turns out. You can find me on Twitter. That's the best way to reach me. I'm at eThomson. I'll also be at the Microsoft booth right after this. You can grab a shiny Git sticker or a Git for Windows sticker, even more shiny. So yeah, grab a sticker or ask me questions. I'll be at the Microsoft booth. So thanks so much. I appreciate you coming out.